Next week, 1 week from today, we're going to have our quiz number 3, and the material is posted on Blackboard for this. This is a quiz on the performance, chapter 6. So we already covered that a few sessions back. Also, we have a reminder of your progress report as a team coming on Wednesday of week 13. So don't forget that, don't wait for long. If I were a member of your team, I would go after every session as a part of studying the material, and I would do the same for my design project. If you do so, you should have all the work done by the time you submit your progress report. Progress report, I got a question, what's the format of that? It's going to be in Word. It's a Word file, so that will make it easier for me to grade, where you will present your design project, from the requirements to the weight estimation, to the calculation of the importance parameters and so on. So these are my 2 announcements for today, the quiz as well as we're getting close to the time of the progress report. Let's wait for couple of more minutes. So anyone has a question?
Yes, Doctor.
Yes.
We had a problem for getting L over D for by airplanes because there are not too much information on the internet that provide L for D.
Yeah, I agree with this. This category of aircraft, you are not going to find someone that will tell you here is the airfoil of the aircraft. But couldn't you find any one, not a single one?
I found a single one, but it was, I think it was high. It was like 19.
What's wrong with that?
I think it's too much high.
Why?
I think the range should be from 14 to 17. I think 19 is high. Or
depending. Well, we have airfoils that can generate more than 20. The point is, it depends on the application. So you will find some aircraft generating more than others. So I wouldn't exclude the 19. That's not bad. That's not very, that's not too high. Okay. Typically, you would be able to find 2, 3, 4, and then we compare. But if you cannot find other than that, then that's fine. I would go with that one. So mention the airfoil. What's the airfoil, and what's the L over D of that airfoil that's being used?
Okay, thank you.
Now, if I don't have any information, I would visit a library of airfoils, and I will see, for example, 4-digit series. Probably the aircraft. What type of airfoil? Do you remember the number?
No, I don't remember.
Okay. Typically, if you want a high lift airfoil, it would be a 4-digit series. So I will go and look at 4-digit series, and I would try to figure a good one. But in this case, yes, I agree. But 19 is not too high. Feel free to use it. But that's for the airfoil. For the aircraft or for the finite wing, you will have to multiply by 0.9. Don't forget that.
Okay.
Okay? And that's without the flaps. If there is a condition on the takeoff distance, the flaps have to be included as well.
Okay, thank you.
Okay. Any other questions?
Doctor?
Yes.
Is there a website or something that we can search about the information in same kind of plane in the project?
No, because when you start doing design, the client will give you his requirements, and he will not give you where to look for the requirement. So
no, I mean, if we want to assume something, we have to search about plane يعني متقاربة أو
yes
أي، بس ما لقينا نحن طيارات يعني ما لقينا موقع فيه له يعطيني المعلومات مثلا اللي هو empty weight over gross weight يعني
No.
بعض المعلومات حصلناها في ويكيبيديا.
No. Let's give me an air. Do you know the airplane type you are looking for?
لا كنا نبحث على ايروباتيك نفس اللي في البروجكت حقنا، فكنا نحاول نجيب طيارات نفس الفئة عشان نقدر نعرف تقريبا الريشيو.
Good. Okay. Let's take this example that you said. The search doesn't have to be a single visit and you will get everything that you want. For example, you will search first aerobatic aircraft. So the first search will give you the types of aerobatic aircraft, right? So let's say I picked one. Do you have one in your head that you want the data for aerobatic aircraft?
No. Any plane we search about multi 3 or 4 and we
okay, give me the name of one. Give me the name of one of them.
Okay, give me 1 minute.
Let's say the Sukhoi 29, Su-29, okay? So you will not find Su-29. Let me share the data of that Sukhoi with you on the screen now. Let me just go in there. Let me share my screen right away. Okay, so you see my screen?
Yes.
So that's an aerobatic aircraft. You made a search and it showed you that Sukhoi 29 is an aerobatic aircraft in the same category. So
yeah.
And you want to find the empty weight to the total weight. No one is going to give you that ratio, but if you scroll down, let's say that's not like a sophisticated site, that's Wikipedia. Okay, so do you see here where is the empty weight?
Yeah, I mean we take the information from Wikipedia. My question, is there any website or something except Wikipedia? Or,
yeah, there are. Just search for you'll find hobby sites all over the place. Aerobatic sites all over the place. So anyone you find the manufacturer data, and it's not going to be much from there, much different from what we've seen here. So if you have the empty weight and you have the maximum takeoff weight, all you have to do is to divide, and you will get a ratio of 0.7, right? 760 over 1.1 thousand. It's about 0.7. Okay, so you can use this.
0.69.
Oh, okay.
Yeah.
You can go to manufacturer data, search for the manufacturer, Sukhoi company, what's the company, and go to the data, and it will give you. It's not going to be much different from here. So here is another one, Sukhoi 27. So you can visit the manufacturer Sukhoi, and that's the original data. Find their website. Company, whatever. Find the website, and they will have the catalog of all their stuff. Okay, here it is, Sukhoi Civil Aircraft, and you go and visit their products and get the information. It's not going to be much different from what you found in there. Okay,
thank you.
Okay, so back to what we're doing here. Okay, so any other questions for the design project? So hopefully by now the team is able to do the total weight of the aircraft. You should be estimating the total weight. Wing loading, we did that last time. L over D, we had that. And today, inshallah, we will be continuing on other parameters. So we will continue today on the thrust weight ratio. Now, anyone remembers from last time? How did we calculate the wing loading? We used two conditions of the requirement to calculate the wing loading. Which two conditions of the requirements that you see on the screen now were used to get the wing loading? Please write them in the chat box. Okay, can you write it down? Yeah, the wing area is what we got from the wing loading. Yes, the definition of the wing loading is the weight over the area. That's correct. But we don't know this when we start designing the aircraft. We get this ratio by satisfying two requirements. Stall is one of them, as Mu'taman said, and what's the other one? Out of the requirements that you see on the screen, we used, well, T over W. There's two problems with this. One, it is not a requirement. You don't see T over W here, right? So we don't see it. It's not a requirement. Range is not an issue because the range does not depend on the wing area. Remember, when we say wing loading, we mean mainly the weight and the wing area. Range does not depend on that. Range depends on how much fuel the aircraft is carrying. So landing distance, yes, not the takeoff. What's the problem with the takeoff? Takeoff, you need a big wing and you need the engine. Since we have not designed the engine, I cannot use the takeoff. So last time we used the landing distance to get the wing area or the wing loading, and from it we got the wing area, and we used the stall speed. Okay, and we got the stall speed from CLmax with the flaps. So we use these two conditions to get a wing loading of about 29. That means the total weight over the wing area is 29, and we know the total weight 5,100. Today we are going to use other requirements. We will satisfy them in order to get remaining unknowns in the aircraft, which is the engine. So the objective of today is that you walk out of this class knowing what is the power of the engine. In order to do this, I have to pick the requirements that depend on the engine. So out of the requirements that you see on the screen, which ones depend on the engine? In addition, maybe to the wing area, but we already know the wing area now. So which requirement depend on the engine? Can you write it in the chat box? Yeah, thrusts, it depends, of course, on the engine, but again, it's not a requirement. You don't start from the thrust because you don't know it. Yes, rate of climb. Rate of climb of 1,000. What is the engine that will give me a rate of climb of 1,000? So that's important. Yes, we will definitely today use the rate of climb. What else? Is there any other condition that depends on the engine? Something in order to satisfy, you need a powerful engine. Yes, the takeoff distance. Takeoff distance depends on the engine. In order to take off in 2,500 feet, I must have a certain engine power. So number 7 and number 4. And may I add to that, not the ceiling, because the ceiling is how high the aircraft will go. This has nothing to do with how fast it can go, right? You can argue that it depends on how big the wing is. Okay, so the other condition is the maximum level speed. Your car will go faster if you have more powerful engine. It's as simple as this. So the maximum speed and the rate of climb and the takeoff distance, 1, 4, and 7 are the requirements that we need to satisfy with a certain engine. One way to do this is to go and ask myself, okay, I will get the equation of the maximum speed, and from there, hopefully I will get the power. I will get the equation of the rate of climb from chapter 5, and from there I will get the power, and the same I will do for the takeoff distance. And when I do so, I will get 3 different values of power. In order to satisfy all of them, I must pick which power. Is it the highest or the lowest or the average? If I calculate the power from condition 1 and 4 and 7, I will get 3 different values. Should I pick the highest or the lowest or the average? Of course, the highest. So I have to pick the highest power in order to satisfy all of them. That's what we will do today. Okay. What remains in this class is just we're going to pick the right equations from the right chapter, use the right values, and we will get the power. They are all equations that we had before. We are just going to use them here. In a way different from the way you used to solve problems, because we are not solving problems, we are designing. So here we will know the left-hand side and we want to find the power on the right-hand side. Let's see how we're going to do this. Let's start with the maximum level speed. And if you have any questions, that would be a good time to ask before we start conditions 1, then 4, then 7. Okay, so we'll start with the, with the takeoff distance, not with the speeds. Okay, with the takeoff distance. With the takeoff distance, if we go back to chapter 6, you're going to have a quiz on this in about a week. You will find that the takeoff distance consists of the parts when the aircraft is on the ground and when the aircraft is airborne. The part when the aircraft is airborne depends on the radius and theta, and this will depend on stall speed only. But when the aircraft is on the ground roll distance, we had an equation for that from chapter 6, which has wing loading CL density T over W. So remember, in here I should know the left-hand side and I need to get the thrust-weight ratio or the power, the thrust or the power, and we can find one if we know the other. So what I know right now is that SG plus SA is 2500. That's the requirement that we had. The total distance is 2500. Okay. So in here, let's put SG first. SG, I don't know the exact value, but I know that it is, if added to SA, will be 2500. So let's wait on this for a second. Do we know W over S? Yes, we had it from last time to be 29. Density, sea level, of course, G 32. T over W is what we want to find. So I really have to find CL max before I move any further. Now you can argue that we had CL max before to be 2.3, but that's when we were landing, when the flaps were fully deflected at 40 degrees or 45 degrees. In takeoff, typically the flaps are deflected only 20 degrees. That means I cannot use the 2.3. The CL max will be slightly less. So we will not work exactly as we did in landing, just to find the CL max here. What I mean is that CL max here is not the same CL max in the same SG of landing, because the flaps are not deflected to the same value. So let's find the CL max. Exactly as we did in the landing, but we will do this for the takeoff. The airfoil that we picked had a CL max of 1.7. That was the value. The flaps that we have will give me an extra 0.9 of CL max when fully deflected. So we added that 0.9 back then when we were talking in the landing. But since the flaps here in takeoff are not fully deflected, they are almost half deflected, halfway. Instead of 45, it's 25 or 20 degrees. Then I can expect that I will not get the full 0.9. I will get only half of it. So 0.9 times the ratio of flap deflection gives me about 0.5 or 0.45. That's the extra lift I will get by deflecting the flap 20 or 25 degrees. So the total CL max is 1.9 plus the 0.5, which is 2.2. One last thing, this is for the airfoil. I have a finite wing. Well, we know that the CL for a finite wing is slightly smaller than that for an airfoil. And we need to multiply that by a factor of 0.9, exactly as we did in the landing. So 2.2 times 0.9 is 1.8. So although we had CL max to be 2.3 in landing, it's only 1.98 in takeoff. Does that mean the wing cannot generate more than 1.98? No, it can if we deflect the flaps more in takeoff, but we don't do this because takeoff speed is slightly higher than landing speed. Okay, so we have now CL max to be 1.98. So I have everything on the right hand side now except T over W. So the distance on the ground turns out to be, when I put the numbers, 233 over T over W. And I will wait on this equation for a second because this equation is only for this part. I will work on the other part now. What about the other part? Well, the other part is SA. And I will put the 3 or 4 equations of SA as is from chapter 5. SA was R sine theta, but the theta has to do with the height of the obstacle and R. The height of the obstacle is 50 feet and the R has to do with the stall speed. So the start point in SA is the stall speed. But you'll say, hey, I know the stall speed. It's given 70 miles per hour. Not quite. 70 miles per hour when the flaps were fully deflected, when we checked stall last time. But now the flaps are not fully deflected, so the aircraft will not be able to generate the 2.3 CL, it will just generate 1.9. So the stall speed has to be slightly higher. What does that mean? I will recalculate stall speed here. So there is a stall speed when the flaps were 40 degrees. This is another stall speed when the flaps are only 20 degrees. And CL max is 1.98. This will give me a stall speed of 111. The radius of rotation will be 2006. And if I put it in the equation for theta, it will become 11 degrees. And the horizontal distance will turn out to be 516 feet. Probably you have realized by now that the distance when the aircraft is airborne during the takeoff or landing is always known as a number. It doesn't depend on anything other than the stall speed. Okay, so it's 500 feet. So if this is 516 feet and the total is 2500 feet, then SG should be a little bit less than 2000, right? So now if I know SG, which is the difference between the 2500 and 500, and I know that it's related as 233 TW, the only unknown is the thrust weight ratio, turns out to be 0.11. Here is our first piece of information about the engine. If you want to satisfy the takeoff condition, you need an engine that gives you 11% of the weight of the aircraft, gives you thrust equal to 11% of the weight. Okay. If I am designing a jet engine for this aircraft, that would be the end point of the process here, because I know the weight is 5,000. I will multiply by 0.119 or 0.118. That will give me about 550 pounds of thrust. Now I have the thrust of the engine. And that will be the end of this part here. However, since this is an internal combustion engine, it is not defined by thrust, it's defined by horsepower. As I always say, you go and buy a new car, you don't go to the dealer and tell him what's the thrust of this car. You ask what's the power of the engine of this car. So I need to convert the thrust which I have here to horsepower by multiplying by speed. But since speed changes during takeoff from 0, accelerate, lift off, and then climb, I must pick like an average speed in order to multiply by the thrust to get the power. And we agreed that this speed is 0.7 of the speed of lift, like the average point when the airplane is roughly here. Okay. So 0.7 times 1.1, the takeoff speed as the stall speed, because this is the lift-off speed or the takeoff speed. That would be about 85 feet per second. Multiply the speed by the thrust will give me the power. So I will multiply the speed by the thrust, because T over W is 0.118 times the weight. This is the thrust, thrust times velocity is equal to the power required. So I need an engine that delivers to the air 5.22 times 10 to the power foot-pound per second. This is the unit of power in the British system. If you want it in horsepower, all you have to do is to convert it by dividing by 550, the conversion factor to horsepower. But as a last step before we do this, we will say this is the power that I need to make the aircraft take off. But there are some losses in the power from the time it's generated in the engine, rotate a shaft, rotate a propeller, deliver to the air. So there are losses. So I will probably need slightly bigger engine, an engine that has a propeller, a certain propeller efficiency. And this is one number that we will typically assume. Typical propeller efficiency is about 0.8 or 0.85. That means if you want 5.2 horsepower, then you must get an engine that's a little bit more than this, 6.5. How did I get it? It's the 5.2 divided by the efficiency, because the engine power has to be more than the power that you need. So divided by 0.8 gives me 6.5. So we get an engine with this power, so that after the power goes from the shaft, and that's why it's called shaft horsepower or brake horsepower, it goes to the propeller, it will be reduced to 5.2. So this is the number that I really have to convert to horsepower by dividing by 550. And this gives me 118.8 or roughly 119 horsepower. So in order to make the aircraft take off in 2,500 feet, we use the takeoff equation from chapter 5. We used the CL max from chapter 2, and we used the power thrust relationship from chapter 3 in order to get to the fact that this power is 119 horsepower. So I will stop now to see if you have questions in the power that we found. Yes, Musab.
Can we use thrust given takeoff distance?
Can I use what?
Shorter distance takeoff.
You can. You mean instead of the 2,500, you want to make it shorter, right? 2,000, for example, or 2,200, right?
Yes.
Okay. So of course you can. I will go here in the 2,500 and I will make it 2,200. That means this number here is going to be smaller, right? So this ratio is going to be bigger. It will go up. So this power will go up, and this power will go up, and this power will go up. Of course, you can make it a shorter distance by putting a stronger engine, more powerful engine. You can do that. But in this case, you will have an aircraft that has better performance than the requirements. Well, that's always a good thing, except that you will have to pay the price, right? It will be probably more expensive engine, and it will be heavier engine, so it might lead to a heavier aircraft. So yes, you can, but there is always a trade-off. You have to understand what's the effect of my decision. If you want to make a shorter takeoff, it will be more expensive aircraft. I'm not saying this is a bad thing. I mean, you must know how much more expensive it's going to be, or how much heavier it's going to be. Does this answer the question?
Yes.
Okay. Nawaf?
Doctor, from where did we get the efficiency?
Oh, it's typically assumed. Remember last time when we said in design, we don't go and do a PhD thesis in order just to find a single value. If it has a value that doesn't change much between different engines, we just go ahead and use it. So from chapter 3, typical efficiency of propellers is 0.8. Now, remember, we are in conceptual design. If this is a real aircraft and we will get to the detailed design, maybe later on as a company, I will make a model of the blade and I will put it on the wind tunnel and I will measure and I will check the efficiency, and it maybe instead of the 0.8, it will turn out to be 0.78. And that difference is important, but it's important in the detailed design, not in the conceptual design. Okay.
Okay, thank you.
Any other question? Now, if that was the only requirement, I will pick an engine that has 119 horsepower. But remember, this is only one requirement out of 3. I still have to check the other 2. So let's go on to the second requirement, which was the rate of climb. You said the rate of climb. So for the rate of climb, we will go on to chapter 6, or was it 5? I think it was 5. And we will get the equation of the rate of climb, and we will try to put everything there. Hopefully the unknown will be the thrust or the power. We now know that they are synonyms. I can convert from thrust to power and vice versa by dividing by the speed or multiplying by speed. Luckily for the rate of climb, the power is there right away. So I have the power. I will get it right away. I will get it if I know the weight. Okay, we have the weight. Efficiency of the propeller, 0.8, we know that. L over D max, we know that, 14. Do we have the drag polar, K and CD naught of this aircraft? No. This is not a problem in a quiz where the instructor will give you the drag polar. We don't know what would be the drag polar of the aircraft, so we have to estimate it somehow. We have to find K and CD naught in order to get the power here. The rate of climb itself is known. It is given in the requirement, give me a rate of climb of 1,000 feet per minute. So I know this left-hand side. Okay, so in order to get the P, I must estimate K and CD naught. Let's start with CD naught. One way to do this is just to put a reasonable value, just like we did for the efficiency of the propeller. If you are a student in AE 427, they typically put CD naughts for a propeller aircraft of 0.02. If it's a jet aircraft, they would use 0.015. Okay. Reasonable values to start with. Okay. Another way is to relate that CD naught to the skin friction of the aircraft. This is another way to do this in here. So, for example, from similar aircraft, if I have similar aircraft, or different aircraft, sometimes close, we know that we can find an estimate of the coefficient of friction, such that when it's multiplied by the external surface area of the aircraft, can be related to the CD naught. Now, that's not quite accurate. That's not a very good way to do this, but it's better than nothing. Okay, so if I use this procedure here with a coefficient of friction of similar aircraft, and external surface area of about 4 times the wing area, which is depend on the shape of the aircraft. So for every aircraft shape, not category or type, just the shape, there is an estimate of this external surface area. If I multiply them, I will get a CD naught of 0.017. You could have assumed it 0.02, a little bit less. For your design project, I can assume it's slightly less than the 0.02. I would say 0.017, maybe 0.016 even, because it's an aerobatic aircraft. Should be aerodynamically clean, very smooth on the external surface. In reality, we will not estimate this surface area, but we will do it after we draw the aircraft. Maybe on SolidWorks, I can get the external surface area. But right now, I don't have a SolidWorks. I don't have the shape of the aircraft. So this is one way to estimate that. So in your design project, feel free to assume it, or you can estimate it in this manner if you want. Okay, so that's for the CD naught. For the K, we are not going to estimate, we are going to calculate it, because luckily we had an equation in chapter 5 that relates L over D maximum to the K. So L over D maximum, remember this equation, maximum L over D, 1 over 4 CD naught K. Since we have CD naught now, we know L over D 14, the only unknown here is K, and K turns out to be 0.075. Now, you might get perplexed. We have so many equations. How am I supposed to pick which equation should I use? Well, you have the procedure now in chapter 8, so you don't have to go and look for them. Okay? So now you know how to get the K. You don't need to go back to chapter 5, just mark the equation in chapter 8, and then you are going to have your procedure. So K is 0.075, CD naught is 0.017. Now, please skip this window for a second. I will get back to it in just a minute. So I have K, I have CD naught, we have the wing loading, we have the density, we have rate of climb. So I know everything in here except the power. The unknown here is the power. Yes, Abdullah.
دكتور انت قلت عندنا بروسيجر chapter 8 اللي هو بروسيجر الكونسبشوال ديزاين.
Yes, this is the process, not the flow chart. I mean the example that we are following right now shows you the procedure. You can highlight the equations and follow that in your design project rather than going to chapter 5. Every equation, yeah, every equation here tells you where did we study it, but you don't have to go and get it from there. Just highlight it in chapter 8, and that will be the whole procedure in one place. Okay. Okay, so we know everything now in the equation because I know the weight, I know the efficiency of the propeller. The only unknown here is P. So P turns out to be 362 horsepower. So in order for the aircraft to achieve 1,000 foot per minute rate of climb, it needs an engine of 362 horsepower, more than double that we needed to achieve the takeoff distance. So of course I will forget about the 118 and that will be my new power. This is what the engine should be, 362 horsepower. Okay. And that would be the horsepower if there was no other condition, but we still have one last condition to satisfy. So let's go to the last condition, but before we go there, see if you have any questions. Abdullah, that's a new question or still didn't
لا
know?
معلش نسيت.
Okay, that's fine. Let's go on to the third condition, calculation based on the maximum velocity. We want to achieve a maximum velocity of 250 miles per hour, which is 366 feet per second. What's the power of the engine that I need? So the way to do this is that during the cruise, we will calculate what's the thrust, maximum thrust that I can get, and then I will multiply it by the speed, equate that to the power. So we will go to chapter 5, get the equation of T over W during cruise. Looks familiar, this equation, the one that was parabolic equation, W over S here, W over S here. We know the wing loading, we know K, we know the speed, we know the density. The only unknown in here is T over W. Okay. But there is a catch in here. When you say the W over S, it is the weight during the cruise, not the maximum takeoff weight of the aircraft. It's the weight here, right in the middle of the cruise. It's not the weight here that we calculated as 5,100. So I will spend 1 minute or 2 minutes just to get that weight from that weight. We know the weight here is 5,100. If I multiply it by the ratio W1 over W0 in here, then I will multiply it by the ratio W2 over W0. It will give me the weight at point number 2. If I and that will be 4,900. Some engineers would use the 4,900 as the weight during the cruise, although it changes a little bit. Others would say, no, we want to be more accurate. I will calculate the weight at 3 and I will take the average. Okay, so at 2, the weight was 4,900. At 3, it will be 4,300, and the average would be 4,600. So W over S, it's W in the middle of the cruise is 4,600. Okay, so they will take like the average. So 4,600. Now I know everything on the right hand side. I know W, I know S, W in the middle of the cruise over S, I have it. CD naught, K, everything. Gives me T over W is 0.078. So T over W in the middle of the cruise is 0.078. Now let's work and convert this to power, exactly as we did twice today. So we will multiply it by the weight to get the thrust, then multiply it by the speed to get the required power, then divided by the efficiency in order to get the engine power. Now, which speed? Is it the cruise speed? No, it's the maximum speed. He wants a maximum speed. We want the engine to give me that speed, 366 feet per second. So multiply by the weight, it's a thrust. Multiply by velocity, it's a power. Divide by efficiency, give me a power of 303. So now we have three powers. You want to satisfy the takeoff condition? I need an engine of 118. You want satisfy the rate of climb? I need 362. You need maximum velocity? I need 303. So of course we will choose the 362, the horsepower of 362 to satisfy all of the conditions. Okay. Any questions? You want, yes, Musab.
Is it always in this order?
It's always in this what? Order?
يعني take off أقل شيء بعدين
No, it doesn't. It all depends on the requirements. Let's say you, in a different scenario, the main focus of the design was the shorter takeoff distance. Told you in every design, there is always the most important requirement. Let's say they decided I don't want to take off in 2,500. I want to take off on less than this. Let's say 1,800 feet or 2,000 feet. So in this case, this value might be higher, might be 400. In that case, the determining factor is the takeoff, and the engine will be heavy because the takeoff requirement, not because the rate of climb. Okay, so it's all about the requirements. For example, if this is the design of a jet aircraft, not a propeller aircraft, transport aircraft, like the ones that you get on board all the time, which condition do you think will be critical for the power of the engine, not the power in this case, the thrust of the engine? Airbus 320, what do you think is the most important condition for the thrust of the engine? Takeoff distance? Probably not, because it will be operating from airports that can also operate Boeing 777, so they have longer runways. So probably the takeoff distance is not a critical one. Rate of climb? Not really. It's not a determining factor. The aircraft should not climb very fast. It's not a fighter aircraft. So you'll have to be easy on the condition of the rate of climb because you don't want people to be scared of. Right. So maximum velocity, maybe, if you want the aircraft to get from point A to point B. But there are other requirements, fuel consumption, for example. So depending on the fuel consumption, what type of engine would give me a certain fuel consumption. So is it a high bypass ratio engine? What would be the bypass ratio? 7, 6, 10, depending. So again, my point is requirements change from one design to the other. So which requirement is more critical will affect the parameter you are looking for. Here in this case, it was the rate of climb. Okay. By the way, this is one reason why designers can go back to the client. If you decide that the 362 is way too big, the engine is going to be too heavy. When we go on with the weight of the engine, you can go to your client and say, hey, the problem that we are having is because of the rate of climb. Are you sure it has to be 1,000 feet per minute? Couldn't it be just 900 feet per minute? And in this case, the aircraft weight will go down by that percentage. Okay, so it's in the conceptual design phase. Sometimes requirements are negotiable. Sometimes they are not feasible. Okay. Okay. So let's summarize what we have so far. We have the engine of 362. Now, one last thing when it comes to internal combustion engine is that they lose power as you go with altitude. As the aircraft climb, the air density will decrease, so the power will decrease. If you want to maintain this power of 362, you must find some way to increase the density of the air getting into the engine. And a way to do this is what we call using a supercharger. A supercharger is a sort of a compressor or an impeller that will take the air outside the aircraft and increase its pressure before feeding it to the cylinders, where it's going to be used to burn the fuel, so that the cylinders themselves will not feel the decrease in air in density as the aircraft climbs. Okay. So the cylinders will be able to provide you with a constant power up to the working altitude of the compressor. So I must have, in this case, if you want to maintain the 362 horsepower, you must have a supercharged engine all the way up to the height of 20,000 feet. Why this piece of information important? Because when I go and buy an engine, I will not go and buy an engine that has this power only, but it has to have a supercharger as well. The other option, if I don't want to use a supercharger, is I can get an engine that has a power maybe of 500 or 600, so that when it decreases with altitude, it will give me the 362. And you can see that's not a smart thing to do, because it will be a very big engine that you are not going to be using all the time, but it's very big simply because the aircraft will go high. So supercharger is a very good choice in here. Okay. So that's it for the engine. We can now summarize the information that we had of the aircraft. So far, we gained a lot of information in the past 3 or 4 sessions. We now know what CL max of the aircraft. We only started from the requirements, 5 passengers, certain rate of climb, but now we know what CL max, L over D ratio, wing loading from last time, weight to the power from today. The power is 362, the weight is 5,100, the ratio is 14. And in the process, we got some information. We got like what's W naught, what's the fuel weight, what's the fuel tank, what's the wing area, what's CD naught, what's K, what's the propeller efficiency. Okay, so we have summarized the parameters that we had. Now, I intentionally skipped one parameter that I will go back and just check because and now explain it, because I thought it will be disturbing just to cut our flow information because of this one. This is a sort of an extra information that we gained when we calculated K. Remember, we calculated K from the equation to be 0.075. But someone might go into chapter 2 and say, hey, I had an equation that relates K to the aspect ratio. K was 1 over pi E naught aspect ratio. Can I use the equation in order to get aspect ratio? Yes, of course. Yes, you can. And that's a good way to estimate the aspect ratio. So from there, the equation actually said K equal 1 over pi E naught aspect ratio, where E naught was a factor called Oswald efficiency factor, which was typically 0.7, as I gave you in one of the homeworks or the quizzes, 0.7, 0.6, depending on the aircraft. So I can use this in order to estimate the aspect ratio to be 7. So that's an extra piece of information that we gained. We were not planning to get it here. We were planning on getting the horsepower, but since we got K, I can use it to get the aspect ratio. Okay. So the aspect ratio of the aircraft now is 7. I can use it in here. So now we have tabulated the parameters. We know a lot about the aircraft right now. We can use this information that we have gained starting next time in order to configure the aircraft. I can use, for example, the wing area and the aspect ratio in order to start drawing the wing. And of course, I have the airfoil. I can use the number of passengers in addition to the size of the fuel tank in order to draw the fuselage. I can determine that I can use the total weight in order to determine the size of the landing gear of the aircraft. So next time and the time after, we will be configuring the aircraft. Okay. Any questions? In the horsepower, the objective today, we agreed we reached the value of a horsepower of 362. Any questions on that one? Okay, so inshallah I will see you on Wednesday. Don't forget, please check Blackboard regularly for the reminders. We have a quiz next Monday and we have your progress report Wednesday of week 13. Thank you, Shabab.